The last thing to look at with our little trip into binomials is just these relationships that exist with the binomial coefficients. Now everything starts with the binomial theorem. So basically any problem we want to solve, the binomial theorem is where we begin. And a reminder of that, it's 1 plus x to the power of n, and written in some notation, the general term nck x to the power of k going from 0 to n. And if we were to write all the terms out, we'd see something like this. nc0, nc1x, nc2x squared, all the way up to ncn x to the n, somewhere in the middle there. We put the general term and say, okay, well, all of the terms would look like this. So now we can be asked questions like this. So what is the sum of nck going from 1 to n? So what would they all add up to? So the starting point is the binomial theorem, so I write it down. Then I have a look at it and go, well, what's the difference here? They're asking me the sum of nck. I've got the sum of nck x to the power of k. So if I make a substitution in for x, how can I make them the same? What number would I substitute in? Well, the logical number to pick is 1, because 1 to the power of anything is 1. So it doesn't matter what the power is. So if I substitute in x equals 1, then on the left-hand side we get 1 plus 1 to the power of n. On the right-hand side we have nck 1 to the power of k, but 1 to the power of k is always 1. So there we have, not quite the answer, but almost the answer. So from k equals 0 to n of nck, that will add up to be 2 to the power of n. But that's not what they've asked me. They've asked me from 1 to n. So I need to pull out the term where k equals 0. So I pull that out of the sum. If I substitute into the general term, it would be nc0, and then plus all the other terms going from 1 to n. Well, nc0, well, it doesn't matter what n is, it's always equal to 1, we said. That was one of our rules we had. It always starts and finishes with 1. So if I move that nc0 to the other side and substitute in 1 for nc0, I've got my result. So the sum of k equals 1 to n of nck will be 2 to the power of n minus 1. So it all starts with the binomial theorem, and you compare with what it is they're asking us. This time it's been expanded out for us, but you'll notice we only have the odd ones. So we only want to know what all the odd ones add up. Okay, starts with the binomial theorem. How will I get just the odd ones? Well, we just saw that if we had all of them, when we substituted in 1, it was 2 to the power of n. That's all of them though. I want to get rid of all the even ones. If I choose a different substitution, see, if I want to get rid of it, then I need to subtract. So I need to get some negatives in there. So if I substitute in negative 1, then all the ones with the odd powers will become negative. The even ones will stay positive, because negative 1 squared, positive. Negative 1 to the power of 4, positive. So if I let x equals negative 1, on the left-hand side, I now got 1 minus 1, but on the right-hand side, I've got positive nc0, negative nc1, positive nc2, negative nc3. So all of those will add up to be 0. Simultaneous equations. I want to get rid of the even ones. To do that, we will have to, which way around? We'll subtract them, won't we? So if I subtract number 2 from number 1, on the left-hand side, I'll get 2 to the power of n minus 0, which is 2 to the power of n. But on the right-hand side, I'll have nc0 minus nc0 goes away. nc1 minus nc1, so I've got 2 lots of it. And that pattern will keep going. I've ended up with 2 lots of all the odd ones. Well, divide by 2, and there I have it. All the odd ones will add up to be 2 to the power of n minus 1. Interesting thing is, all the even ones will also add up to be 2 to the n minus 1. That makes sense, because we said Pascal's triangle is symmetric. So yeah, all the odd ones will add up to be the same as all the even ones. K nck. Okay, there's my binomial theorem. Well, I'm going to have to do something more than just a substitution. I somehow need to get the k in front of nck. So we have to think through all the different types of maths we now know. How do I get the power to the front of the pronumeral? This is where calculus comes in handy, because we know that when we differentiate, we put that power to the front. So if I differentiate both sides of this equation, so on the left-hand side, we'll use our chain rule, bring down the power, lower the power, diff the inside. On the right hand side, well, it's just x to the power of k I'm differentiating. The k will come to the front, but the power will be k minus 1. I now have this new expression. I want it to be k times nck. I've got k times nck x to the power of k minus 1. Got to substitute something in for x. Again, I'll just substitute in 1, because I'll end up with 1 to the power of something, which is always 1. So on the left-hand side, we'll have n times 1 plus 1 to the power of n minus 1. The right-hand side, we'll have k times nck. We're going from 0 to n, so we've got a similar situation to that first example we looked at. Our question said 1 to n. So we'll pull out k equals 0. It actually turns out to be 0, because if k is 0, 0 times nc0 is going to be 0. But we have our answer. The sum from k to 1 to n of k times nck is n times 2 to the power of n minus 1. Alright, this one's a little bit more tricky. By equating the coefficients of x to the power of n on both sides of the identity. So they've given us a hint on how to do this one. We're going to look at the coefficients of x to the power of n. Okay. We've got to show this expression. The sum of nck, it's using the alternative notation, but nck squared is 2n factorial on n factorial squared. Okay, starts with the binomial theorem. I'm going to expand the whole thing out here. Now we're going to have 1 plus x to the power of n times 1 plus x to the power of n. And I want to look at the coefficient of x to the power of n in that expansion. I don't want every term, I just want to find the terms with x to the power of n. So in other words, I'm multiplying nc0 plus nc1x plus nc2x squared and so on by the same thing, nc0 plus nc1x and so on. So I want to get x to the power of n. So nc0 would have to be multiplied in the other one by ncn x to the n. nc1x would have to be multiplied by ncn minus 1 x to the n minus 1. Now they're all going to have a pair to match up with, and we want to end up the powers at n, so that would add up to b. So squared will go with the n minus 2. And so on and so on and so on, and eventually we'd come down to the very last one where ncn x to the n got matched with nc0. So the coefficient ends up being this. nc0 times ncn, nc1 times ncn minus 1, nc2 times ncn minus 2, until we got to the last one, ncn times nc0. It's very close to what we want. Now we use Pascal's triangle relationship, where it's symmetric. So actually, nc0 and ncn are the same thing. nc1 and ncn minus 1 are the same thing. The two numbers on the bottom add to give the number on the top. So I could rewrite this as nc0 squared plus nc1 squared plus nc2 squared all the way up to ncn squared. And that was what they were looking for. Well, one side of it was the sum of all those terms. We have the sum from 0 to n of nck squared. But now we have to look at the other side. Well, thankfully the other side's a lot quicker. So 1 plus x to the power of 2n, it's a binomial expansion. Somewhere in the middle there would be a term that would go 2ncn x to the power of n. And it's the only term in there that has x to the power of n. So on the other side, the coefficient is that, 2ncn. But we said these two things were identical, therefore the coefficients must be the same. And there's our proof. So therefore, the sum from 0 to n of nck squared is 2ncn. That's not quite what they want us to do though. Remember, it was 2n factorial, n factorial squared. So now we have to go to factorial notation. 2n factorial on n factorial. N factorial, well that is n factorial squared, and eventually we've got to where they want us. The very first new HSC, there was the question. Basically, that's exactly what we just did in the last example. So they did ask it. It's because they actually turned it into a perms and com question. Because part B came up with this. A club has 2n members with n women and n men. So in other words, same number of men as women. So we're looking at groups that have an even number of members. going to have one man, one woman, two men, two women, and so you'll always end up with an even number of members. Show, giving reasons, that the number of ways of doing this is 2n/Cn. Well, the number of ways of choosing k men from a group of n men. A club has 2n members, n women, n men. So if I just want a group with k men, how do I get them? Well, from the n men, I choose k. But similarly, I could do that with the women as well. So the number of ways of choosing k men and k women from a group of n men and n women must be those two things multiplied together, which is nck squared. So the total ways of choosing the same number from both groups must be the sum of all the possibilities. Now, if there was originally, well, this is a silly one, but if there originally was no one, then I'd choose none of them and none of them. But if originally the group had 2, then I'd choose one from there and one from there. If it was originally 4, because remember it was an even number, well, I'd 2 from this group, 2 from that group. So we're adding up all of those possibilities. But in part A, we just showed that was 2n/Cn. So that's how they related it back to what we did in the first part. But then they said, well, from the group chosen in part B, one of the men and one of the women will then be selected as the leaders. Show, giving reasons, the number of ways to choose the even number of people, and then the leaders is this. So the number of ways of choosing the leaders in each particular group. Well, if my group size is 2k, then I know it's going to be nck squared. So I've chosen the group. But from the group, I now have to choose leaders. So there are k men, one of them is going to be a leader, so I've got k possibilities. There are k women, one of them is going to be a leader, so I've got k possibilities. So the total number of ways would be the sum of all of those different ones. The groups where there's 0, the group where there's 1. Well, hang on a sec. I haven't included k equals 0. Why? Well, k equals 0 is not possible. Because if I've got a group of 0, then I've got no one to choose from. So how do I pick a leader? I leave that one out. It's just k equals 1 to n of k squared nck squared. And so there's all our possibilities. If I was to write it out of some notation, it'd be 1 squared times nc1 squared, 2 squared nc2 squared, so up to n squared ncn squared. But then they kept going. The process is now reversed. So the leaders are chosen first, and then the rest of the group's selected. Now let's find an expression. So we choose the leaders first. So we don't know who the leaders are, we're going to pick them. But we've still got n men and n women. So there must be n possibilities for the leaders, both the men and the women. Then we've got to get the rest of the group. Because we've chosen the leader, our group has n minus 1, and we want to get k minus 1 from that group. So in other words, I now have to choose n minus 1 ck minus 1. So from the n minus 1 I've got left, I've got to choose k minus 1 men. Well, we've got to do the same for the women as well. So essentially, it's the same as we had before, but now instead of nck, it's n minus 1 ck minus 1 squared, and we're multiplying by n squared because we chose the leaders first. We now have this, n squared, n minus 1 c naught squared plus n minus... Well, factorise out the n squared, and I'm left with n minus 1 c naught squared plus n minus 1 c1 squared up to n minus 1 c n minus 1 squared, which we, back in part A, showed it was, well, the one we showed was 2nCn. So for our one now, it's going to be 2 lots of n minus 1, c n minus 1. We end up finally with the expression. So all right, 15D will have a little bit of a play with that idea.